Hello and welcome to today's video. Today we're going to leave the academics of graphs behind and instead focus on three discrete use cases, places in industry where people are using graphs today to solve business problems and challenges. My name is Corey Lanum and I've been using graphs and building applications to use graphs for over 20 years now. I started all the way back in 2000 when I was helping U.S. government intelligence agencies build graphs to help understand connections between terror activities in the Middle East. And it's been very exciting for me to watch the explosion in interest in this kind of technology across a wide variety of domains in both private industry and in government over the last 20 years. I've also written a book on the subject, which goes into quite a bit more detail about the best practices and techniques for visualizing graphs, called Visualizing Graph Data, that was published in 2016. So here's what we're going to cover today. We're going to cover when are graphs useful? When do I have data, and what sort of data lends itself well to modeling as a graph, and when can you get useful results out of that? Also, why should you visualize it? There are many instances where graph data doesn't necessarily need to be rendered in a visualization in order to provide useful insights. And then the bulk of the video will discuss three use cases from industry where they are using graph visualization to achieve powerful results. The first one is from intelligence and law enforcement, which sort of pioneered the concept of graph analytics and graph visualization back in the 80s and 90s. Then we're going to talk about financial fraud, looking at banking and insurance industries and how they can take advantage of their transactional data to uncover potentially fraudulent transactions. And the final thing we'll take a look at is cybersecurity and looking at, for example, packet transfers across a network. When some packets might be infected, something might stand out as being unusual that is worthy of further investigation. And now let's talk about when the data that you've collected might be useful to think about as a graph and to model that way. In some cases, data works very well as a graph, and in other cases, it's not particularly helpful. So, for example, if you are a retailer and you have a list of products and their SKU numbers, it's not that helpful to think about that as a graph because each product is linked to a single SKU number and each SKU number is linked back to a single product. It's just a table, and it's usually more helpful to understand it as a table. However, in the same scenario, if you have a list of customers and the products that they've bought, now it does start to make sense to think of this perhaps as a graph because you do have that many-to-many relationship inherent in your data. Each customer likely bought one or more products, and each product was likely bought by one or more customers. So that many-to-many relationship can reveal itself via a graph and via looking at it as a graph. And it's useful to think about these things as a graph when you care about those connections, when I care about the relationship between a customer and the products that they're buying. Each data set can be modeled as a graph likely in very different ways, depending on what you choose to be your entities or your nodes and what you choose to be your links. So the modeling can have a profound effect on how the graph looks and what sorts of things you can learn from it in the end. Over here on the right-hand side, I've taken a graph of rented bicycles in New York City, where the stations are the nodes and the trips between them are showing that a person rented a bike from one station and returned it to another. And we can see, without even labeling the stations on the nodes here, that there are two distinct groups of activity. The very tightly connected group in the center of the chart is Manhattan, and the slightly less dense group on the lower left-hand side of the chart is Brooklyn. And you can see that most trips remain in the borough where the bike was rented. It's just returned to another station within that same area. You can also see that there are a fair number of trips between Manhattan and Brooklyn. Now, the nodes that are around the outer edges are from the outer boroughs, and you can also see that there are fewer trips that result in people riding their bikes from those outer boroughs into Manhattan or Brooklyn, and they mostly stay in their own neighborhoods. So this sort of data, modeling it as a graph, shows us some interesting things in the pattern, in the visual pattern of what we're looking at, even if we're not actually drilling down to the individual data. I also want to talk about why we might visualize graphs. Allowing users to explore their way visually through graph data can be a very powerful technique to allow them to uncover interesting things about the data. But it's not always the most useful way, even if you are actually using graphs. An example I like to use is a recommendation engine. Recommendations engines are often built on top of graph data. So, for example, when I'm watching Netflix, it might show me examples of other Netflix shows that I might want to watch based on what other users like me have been watching. However, when I'm watching Netflix, I don't want to see a graph of me and other viewers to see what shows they've watched and have to pick my way through that to see what the algorithm might recommend. I just want to see the recommendations and watch the show that might appeal to me. In that case, there likely is a graph underpinning that entire recommendation engine, but the user doesn't want to, and it wouldn't be useful or even legal in many cases to actually show that to the end user themselves. And there's two different use cases here for visualizing graphs. A lot of people will think about their data model itself as a graph, which is true. So if I am creating a model based around some data I've collected, I might have a person and their email address and their home address, and I might want to draw that as a graph. So over here on the left-hand side, we're showing the model. I've got people connected to email addresses because they use those email addresses. I've got people connected to home addresses because that's where they live. I think it's much more interesting, and you get a lot more power out of graph visualization when you're looking at the actual data in the data set and not just the model of it. So in this case, we're looking at me, my email address, the one that I use, and my home address. Because then when you start adding multiple people and multiple addresses and multiple email addresses, then you start to uncover those patterns. So there's much more value in showing the underlying source data as a graph than there is just the model itself, although the model itself can be a good place to start. So now let's dive down and start taking a look at how this type of technology can be used in the real world on real-life data sets. So as I mentioned at the beginning, I spent the first part of my career in the early 2000s working for U.S. intelligence agencies and trying to help collate information from many disparate sources into a single coherent picture of what was going on in the world. And those sources are from various different domains, like signals intelligence, where they're interpreting signals that they're taking off of out of the air, for example, or off of wires. Human intelligence, what their informants are telling them in various countries. And open source data, what they're finding in various databases across the globe. And they need to turn that into a single narrative about what's going on in the world. And to do that, they started using graphs. And this was 10 or 15 years ago. By modeling this data as a graph, they can help use that to make predictions about what might happen next or who might be involved. So what we're going to do is we're going to take a look at some real-life data assembled by Mark Sageman in 2004 of terrorists in Al-Qaeda and how they're connected to one another through the global network of Al-Qaeda terrorists. So what we have now is a graph of those terrorists and how they're connected to one another. We've rendered each person as a node, and the link between them shows that they're connected somehow, either via a known association or because we've intercepted communications between them or something like that. And we've chosen to render them in a certain way. So the person themselves are the node. We've used an ornament on the node icon to show us what country they live in. We call that a glyph. And if we take the zoomed out view here, we can start to see some interesting patterns, even without looking at the individual detail. So there's a group up here that's very tightly connected. So everybody's talking to everybody else. And if we zoom in, we can see that they are mostly from the country of Malaysia. We can see who they're connected to within Malaysia, but then we also notice that this one person, this one node, is responsible for connecting most of that Malaysia subnetwork to the rest of the network of Al-Qaeda terrorists. That's pretty visually apparent when we look at the data. So we can then drill down and see who this person is. But if we're interested in this data, maybe not at an individual level, there's 220 nodes on this chart, so it's a bit much to consume all at once. Perhaps we want to take more of a geopolitical view. And this is one of the things that we do in a lot of our different networks that we build, which is a feature that we call Combine in our product. But it allows us to group together nodes and look at how the groups themselves are connected to one another. That allows us to take sort of a summarized view of the data. And so that we get a simplified chart with the abstractions, but not the detail. So let's do that now. Let's group them together. Now we're going to do that by the country that they live in. So now that we can see how the countries themselves are connected to one another through their Al-Qaeda networks. And I do have a simplified or summarized view of the data. I have nodes now that represent the country. This is a different model of the data than what we were looking at previously. As I mentioned in a previous slide, you can model your data in very different ways that gives you a different visualization. We've also sized the node to show us the number of individuals inside of each country. So the larger nodes have more terrorists in them. Now, this is a summarized view of the data. We learn a little bit about how the countries are connected. There's a much stronger link, for example, between Afghanistan and Malaysia than there is between Afghanistan and Morocco and things like that. But we do have access to that underlying source data too. So if I wanted to zoom in, say, on France and look at the individuals inside of France, I can do that. And now I can see the people who are living in that country, how they're connected both internally within France, but then externally to other countries on the globe. So Zacharias Moussaoui here has connections to other people in Europe, Pakistan, and Malaysia and Singapore as well. So we call this feature combined because it allows us to group together nodes, still have access to the underlying source data, but you're not overwhelmed by looking at every node and trying to render every individual data point on the screen all at the same time. The other thing we may want to do here is to do what's called social network analysis, and that allows us to run some algorithms on the underlying source data and display the results of those visually. So the one I'm going to run for you now is called betweenness, and what that does is it looks at how often is a particular node on the shortest path between other nodes on the chart. So if we think of this network as being communications between terrorists, if someone up here in the Malaysia subsection of the network needs to communicate with somebody down here, maybe in the French section of the network, then how are they going to get that message across based on who they know? And how often are people on that message pathway? Because those people tend to act as conduits or funnels of information as it flows across the network. So if we run this betweenness calculation, which I'll do now, sizing the nodes by its betweenness score so that the larger nodes stand out and we can identify on the chart which ones they are. So you actually get to watch the nodes grow, and now we can see, for example, that Osama bin Laden, unsurprisingly, has the highest betweenness score. He's the leader of the organization, and most people have to go through him. But some other nodes stand out too, such as this Malaysian individual that we looked at before, Ansep, is a larger node than all of the surroundings because he is the one responsible for communicating between that Malaysian subsector and the rest of the network. So things like social network analysis can give you really powerful insights into what's going on in your graph and allow you to understand better which nodes to focus on. In our node link visualizations, one of the things we're not able to understand quite as well is the timing of things. So when we were looking at our Al-Qaeda network, we didn't know whether those communications we had intercepted were before or after others, or we didn't know whether they were clustered in time very closely together or perhaps years apart. So a timeline analysis of connected data is another way of looking at the same connected aspect to the data, but to get a different dimension to it. So here we're looking at 40 years of terror activity around the globe, and we see a timeline which is showing that from left to right. I can zoom in on a certain window of time. So if I want to focus, say, for example, on September of 1995, I can see which terror groups were active in which countries at that point. Or I can drill down into a specific country and see what sort of activity was going on, for example, in Ethiopia or in Mozambique during that time frame, and I can see when they were active. So a timeline analysis gives us another dimension in the ability to understand the sequence of events or clusters of when certain things happened and how they might be connected to one another. The next use case we're going to discuss is anti-fraud. Now, fraud is a particularly good example where graphs are helpful. I should say anti-fraud. We're in the business of trying to prevent fraud, not to commit it. But the definition of fraud is misrepresentation of a relationship for financial gain. I could pretend to be somebody whom I'm not in order to gain access to someone's bank account, or I could artificially create entries in a ledger that aren't there. And by looking at that data as a graph and by visualizing the big picture, the fraudulent relationships or the fraudulent transactions are going to stand out often because they don't match the normal course of business. And I can identify those visually and drill down to determine which ones they are. So let's take a look at an example of that. The first example we'll look at is a car insurance fraud example. Now, in this view, we've modeled the data as a graph and we've brought it into the visualization exactly as it is modeled. So for example, if it's in a graph database, this is likely how you'd store it. So we have different entity types, things like policies, people, we've got claims, we've got the vehicles that are insured. When there is a claim, there's various damages associated with it and so on. Now, you can start to see some clusters some interesting things going on in this data from this view. For example, this particular body shop is involved in several different claims, but that may not necessarily be unusual. It might just be one that is a busy place that's large and is near a lot of insured. But by doing what I mentioned earlier, how we can change the model of the data, which changes the way it's visualized, we can start to uncover some more interesting things here. So what we're going to do instead is abstract out all of the policies and claims and all of the damages and things like that, and just look at the people themselves. So two people have a link between them if they have anything in common, if they share a vehicle, if they share a policy, or if they share an address. So it's still a graph, but it's a very different model of the data. Now, if we look at here, we see some pretty interesting examples. So for Neville Cameron is linked to a lot of different people in this example. So linked to various doctors who are doing treatments on people who are in accidents. He's linked to people who are witnesses. He's linked to people who are insured, and so on. And then we have a doctor who herself is linked to a lot of different people who are all seeking treatment at the same doctor. So both of those might be reasons to focus our investigation or pay closer attention to some of these individuals who have a lot of connections. And the next thing we might want to do is to take a look at the geography of this data. So graph data often will have some sort of geographical component to it. This example is out of the UK, and we're looking at where these people live and where they're getting their autos repaired. And you would expect that when somebody's in a car accident, they go to a nearby mechanic to get the repairs. But in this case, we're seeing a lot of what we expect, people going to nearby mechanics, but then we also see a large number of insured going to the same mechanic who is nowhere near where they live. So that may be another way of looking at this data. We can superimpose those nodes on top of a map, and the longer links in that case have a physical correlate. Those are the longer distances traveled by the individuals to get repairs to their cars. The final thing we'll look at too is the damage types. So we might want to create a graph model which is showing just the mechanics and the types of things that they're working on. So you would expect an auto body shop to have a wide range of things that they work on and a wide range of damages. And that is the case for most of these. If we click on one, we can see that this person worked on 4 rear doors, 3 mirrors, and so on, what you would normally expect. But if I click on this Fraser's one, I can see that they are linked to 14 different rear door repairs and very few others, only 2 or 3 of the other types of repairs. That's more evidence that this might be a place I want to pay attention to. I can both see that people are traveling a long distance to get to this mechanic, and that this mechanic is doing an unusually large number of repairs to the rear door, perhaps because that's a particularly profitable one, or perhaps because that those repairs are being fabricated. So in this insurance example, we're using different graph models to expose different dimensions to the data to try to uncover what might be fraudulent. In our next example, we're going to look at a traditional node link representation and a timeline representation side by side to be able to uncover information about a money laundering scheme. So over here on the right, we've got our node link representation, which is showing us various deposits out of cash deposits to a casino, into various bank accounts, and then into the individuals who own the casino, and so on. And we're trying to figure out where the money went or how the money flowed. So the graph, the node link, is a great way to show that, what accounts are linked to what other accounts. But what it doesn't tell us is when those transfers might happen. And if they happened years apart, that's a much different scenario than if they happened one right after the other. So the timeline over here is telling us when the transfers happened. And you can see that the two interact together. So as I highlight a particular transaction on the timeline, I'm showing where that is on the graph as well. The other thing I'm doing here is I want to highlight risk scores. So I'm using what we call a donut on the chart to highlight how risky a particular account is based on some sort of automated algorithm that's running behind the scenes. But I'm also taking that same color and applying it to this node over on the timeline too, so that we can pin and focus on, say, just transfers in or out of that high-risk checking account. And I can see the cash deposits coming in, and then I can see the transfers going out. So for example, if I highlight this $7,500 here, I can see that that was a single transfer that took place on July 14th, 2021. If I look in the opposite direction of the $8,900 going from the account into the trading account, I can see that that actually was several different transfers all taking place within a few days of each other in June of 2021. So by looking at both the timeline and the link chart in tandem, and being able to interact between the two, I get another dimension, or a really important way of understanding what's going on in this data set. The next example we're going to look at here is cybersecurity. Now, cybersecurity can mean so many different things, from threat detection to threat investigation to endpoint hardening to analytics, and all of those involve a graph in many cases at the back end. And the reason why is because a TCP/IP network ultimately is a graph on many different levels. So layer 0 with the actual physical cabling is connecting devices to other devices with actual wires. Those links are real physical things in the real world. And all the way up at the application layer too, which devices are hosting which applications and which servers and things like that, is also a graph, and you can also model that as a graph. So what we're going to do today is we're going to take a look at individual packets as they flow across a network. We just took a snapshot of a specific network over the course of just 10 seconds to look at how those packets are flowing, what various domains they're going to, and see what we can learn from that. In this instance, we took the graph of a single network-connected device, Dan's MacBook Air, and plotted it against all the IP addresses that packets are flowing to and from on that address, both on the graph on the right and on the timeline on the left. Now, if we want to see specifically what was happening when, we can see up at the time bar here at the top, about 10 seconds flow between the beginning of the time frame where we were capturing packets and the end. If we zoom in on a specific window of time, we're filtering to show only the IP addresses that were hit during the time frame that we've selected. So for example, we can see Dan's MacBook Air going off to one server here, getting the result back, going to another server here, getting a reply back, and so on throughout the time frame. We're also filtering the graph when we do that. So over here on the right, we can see only the IP addresses that were connected during the time frame we have selected. And this makes it very easy to talk back and forth between the two components, the timeline and the node link visualization. Another example we're going to look at here is data breaches. So we've created a graph where the nodes are the people or groups responsible for the breach linked to the company that experienced the breach. We've color-coded the link between them via the technology that was used to commit the breach. And then the timeline down here at the bottom is showing us when those happened. One of the most important things when working with graph visualizations is the ability to take a large volume of data and filter it down to the smaller bit that's relevant to an end user so that they can focus their investigation on the bits that they want to pay attention to. So here we have two different ways of filtering in the same application. I can see a spike here in September of 2013, and as I zoom in on that spike, I'm filtering my graph to show me only the data breaches that occurred during the window I've selected. So I can see that activist groups were responsible for a significant number of the breaches in September of 2013. The other way I could filter is by looking at that technology. So we can say physical access, for example. This is where whoever committed the breach had physical access to the server and perhaps downloaded the breached data onto a third device and then distributed it that way. If I select that, now we've filtered both on the time bar and on the chart only those breaches which had physical access as a component of the breach. So we can see when those happened, if they differ for some reason from what we were expecting or all of the data on our chart. And we can also see what types of people are responsible for physical access. And we'd be unsurprised to find that it's mostly end users or system or network administrators, because those are the ones who do likely have physical access to the servers required to commit a breach. But then we can see which companies are responsible or have had breaches in that time frame. So, for example, the U.S. Postal Service or the Internal Revenue Service had breaches during that time window committed by physical access to the servers. So now I want to take a few seconds to talk about the tools that I've used to build the visualizations that we've shown you today. So here at Cambridge Intelligence, we have 3 products, 2 for graph visualization and 1 for timeline visualization. The graph applications that I've shown you have been built using Keylines and Regraph, which are both toolkits that you can embed in your web application. One is with a JavaScript API, and Regraph is with a React API. And the timeline tool is Chronograph, which can also be embedded into a web application for a timeline view. And the 2 products, Chronograph alongside Keylines or Regraph, can work together. These are toolkits that are available to try and also to license to build in and bundle into your web application for your end users. So do feel free to reach out to us if you want to give these toolkits a shot. So let's recap what we've learned today. The first is that connected data is everywhere. You probably have some sort of graph component to your data, and it's really important to model it in a way that provides you with interesting insights when you visualize it. The graphs help you tell a story because you can create a narrative around the data that you're showing, and you can allow your users to perhaps even predict the future by looking at patterns in the past. Timelines are a really important component to graph visualization because you need to understand the when and not just the who and what's connected to what else. And then the visual appeal, looking at these things, needs to be powerful. You need to better understand what you're looking at by tying visual properties of your graph to physical properties of the data that you're collecting. So I hope that you've enjoyed the video, and if you have any questions, do feel free to reach out to us. Thank you very much.